Simon responded that he's lived in the Saranac Lake area in the Adirondacks all of his life. He studied astronomy and physics at Haverford College, where he was inducted into the Phi Beta Kappa. He was awarded the Lewis B. Green Prize. Now I'm supplementing somewhat from his resume. He was awarded the Lewis Green Prize given to students who demonstrate excellence in research and go above and beyond in contributions to the department. He was awarded the M. Agenberg Endowed Scholarship in 2024. On further review of his resume, these details stood out to me. I noted that he was a core member of the Earthquaker Action Team, which organized roughly 5 environmental protests and events per year in the Philadelphia area, including a week-long protest march with over 300 participants. Currently, he is Associate Director of Astronomy Outreach in the Adirondack Sky Center and Observatory in Tupper Lake. He is starting a PhD in astrophysics at Tufts University this fall. Let's welcome Simon and honor both his academic achievements as well as his commitment to our greater good.
Hey, everybody. Thank you so much for that introduction. It's really great to be here. If you give me a second.
I mean, I've stopped sharing, so you should be able to share your screens. There we go.
Yes, there we go. Thank you all so much for being here. Thank you for having me. Very honored to be here. Yes, as you mentioned, I'm the Associate Director. I work at the Adirondack Sky Center and Observatory. If you're not familiar with us, you should be. We do a lot of cool things.
Okay.
Is everything okay? Do you need me to change anything? Okay.
Jackie needs to mute, so we're not hearing room noise.
Yes.
Okay.
Yes.
If you're not familiar with the Adirondack Sky Center and Observatory, you're missing out. We do a lot of really cool activities. We host free stargazing nights. We have a portable planetarium we bring around all throughout the Adirondack Park and beyond. We host summer camps. This is a rocket camp we hosted last summer. And we have a recently opened robotic makerspace. So it's a great focusing on astronomy, but really STEM experience for all ages. I wanted to highlight some of the things that you folks might be specifically interested in. We host an annual astrophotography conference. I don't know why the dates aren't here. They must have gotten cropped out. I do apologize. This year they will be, it's the first new moon of October, which I believe is the 18th. I apologize for missing the dates. But check out our website, adirondackskycenter.org. You can find more information about this astrophotography conference. Last year was my first year being a part of it, and it was a great experience. It's a really warm, welcoming environment. We welcome people with all levels of experience, so I have no doubt that everybody on the Zoom would fit in very comfortably. And it's designed to give people the skills and give people as much hands-on practice taking photographs of the night sky, building their catalog and building their skills. We focus on both taking the images and then image processing over the course of 3 days. It's very intensive, very fun, and it's a really warm, welcoming environment. If anybody here has joined us for that astrophotography class or conference, I'd love to know. So put that in the chat. I think I see some familiar names throughout. We also regularly host our own talks. So if you are in Tupper Lake on July 11th at around 7 p.m. and you enjoyed my talk today, Professor Ken Olam is going to be giving a talk about observing the universe with gravitational waves, which is sure to be very exciting. Other than that, we have our own Cygnus series of online lectures, not to compete with this online lectures, but we host those regularly. So check out our website for those. And David Bishop, big thank you to David Bishop. He gave a talk in January. And you can find that talk on our YouTube, again, linked all from our website. So that's, thank you for allowing me to plug the Sky Center a little bit. I hope that you all continue to engage with us. I see there was a comment. Do you place your talks on Zoom? Yes, yes. So that talk, this talk will only be in person, unfortunately. Most of our talks are virtual on Zoom. And they are also recorded, and we have a YouTube series, YouTube channel where we post those. I don't think that we don't have any planned virtual talks in the next month, but they will be starting up again in August. So join our mailing list, check us out our website. We regularly host a bunch of free activities, many of them virtual. Astrophotography is not virtual. But yes, so today I'll be talking about cosmology. Whenever I give a talk, it's always a debate between how should I title it? Should I make it a little bit more academic, a little bit more scientifically accurate, or do I make the title a little bit more flashy or a little bit more interesting? You guys seemed like a really sophisticated audience, so I went with a more academic title, The History of Cosmology. If I wanted to do a flashier title, maybe I would have chosen The History of Everything, The History of the Universe. Or I could have said The Universe, how did it begin and how will it end? That's not very scientific. That wouldn't be scientific of me. My academic advisors would point their fingers, waggle their fingers. But that is, in broad strokes, what cosmology is. It's the study of the cosmos. It's the study of the entire universe. The celebrity of the field, you might say, is the Big Bang. That's the event that people are most familiar with. So if someone asks me what I study and they are just looking for a few words, I say I study the Big Bang, even though the field of cosmology encompasses a lot more than that. Also, I mentioned that I'm getting a PhD, starting a PhD in September in astrophysics. My research will be on cosmology, so I will be studying the Big Bang and other related topics that I'm going to talk to you about today. And it's really interesting. So thank you for allowing me to share my field and my love for this field. So you might have noticed. Oh, and before we begin, a little bit of housekeeping. Please feel free to type any questions in the chat at any time. Whenever you have a question, just type it in the chat. I'll check the chat regularly and answer questions as I go. And then I will also pause for questions at the end where you can unmute and ask questions during that designated time period. But yes, so just in my little intro, I mentioned the words cosmology, or I'm sorry, cosmos and universe. And I've kind of used them synonymously, but I wanted to talk a little bit more about the difference between what is the cosmos and what is the universe. So the universe, if I had to describe it in a gesture, I would do it's everything. It's all of this. If I wanted to be scientific, I would say the everything that we can interact with, everything that we can see, touch, interact with, all the matter and energy, all the radiation, and everything within our local, everything that we can that we are made of and we can interact with. Less physical, you could say like the material realm. That's more metaphysical or like mystical, but it's kind of everything. It's the universe is the materials that make up everything. It's kind of hard to describe. And I'm realizing just this now. Cosmos is slightly different. So cosmos also it means the universe, but it also signifies an interconnectedness of the universe. So it's all the material in the universe and how it's connected. Cosmos implies interconnectedness and order. It's a Greek word, and it is the opposite of chaos. So chaos would be a disorder, cosmos would be bringing things into cosmos, into order. So cosmology is the study of the universe, but it's a physical study. It's a branch of physics, it's a branch of astrophysics, that deals with how things are connected. And I wanted to, because this is the history of cosmology, I wanted to give a brief nod to ancient cosmologies. So in ancient stories, ancient kind of creation mythologies, ancient religions weren't really concerned with how the universe, how the world came to be, as in popped into existence out of nothing, as we kind of think about today. Ancient traditions really described the world, the material realm, as always existing, but it had previously existed in a state of chaos, in a state of disorder. So, common thread, this is a generalization, but a common thread across many ancient religions and ancient mythologies was that the world used to exist as a vast ocean, a chaotic ocean. And then what happened is you would have a deity, a god, come in, and they brought order, they brought cosmos out of that chaos. So in this example, we have the god, this is a Babylonian god, Marduk, who's fighting the ocean monster, Tiamat. This winged monster on the left signifies chaos. It signifies the watery, chaotic ocean that the world, they believed the world used to be. And then Marduk on the right is the creative god. He's the god who created the universe. And ancient mythologies were interested in, and this creative act was really a separation. So Marduk in this story and many related stories, the deity brought order to the universe by separating, for instance, the ocean from the land, light from dark, summer from winter. So a common thread across many creation traditions and religions is this separation of chaos from order. So these questions of cosmology, how we get order in the universe, are some of the oldest questions that the human race has been grappling with. So in cosmology, we ask, where did all of this, capital all, capital this, come from? How, why is it here? And what's going to happen? And where is it going? What is the origin and end of the universe? So these are ancient questions that people have been grappling with for a really long time. And we are still asking them in the modern day. So modern day cosmology is a scientific field. So we use the scientific method. And some of the questions that we might ask, these are very, very general, broad questions, did the universe have a beginning? A more colloquial way of framing this is what was around before the Big Bang. If you're familiar with the Big Bang, we'll talk about this more later in the show. Some other questions are, what is the universe's shape and composition? If we're talking about the universe as a system, what is its shape? What's it made out of? And what does it look like? Talk about that more in a little bit too. And then how will the universe end? What's its ultimate fate? And will it end? These are all big, important questions. I'm going to give you a spoiler. I'm not going to answer any of these questions in my talk, and we probably won't answer these questions in my lifetime. And that's a good thing. It's a good thing for me, at least, because it means that I still have a job. If we answered all of these questions, then the field of cosmology would be over, and there'd be no more use for cosmologists, and I would no longer receive funding. But what I'll be talking about in this talk is how we've made strides and where we've come from and the kinds of things that we know. So although we can't answer these questions for certain, there are many things that we know. Just going to check the chat. Great. I wanted to show a quick video about the scale of cosmology. So cosmology is a scientific field, and like any scientific field, different scientific fields will deal with different scales. So a microbiologist deals with microscopic things that you need a microscope to see. Um, an oceanographer deals with the entire ocean, so things on the scales of millions and millions of acres. And if you asked an oceanographer, well, what are these individual water molecules doing? They'd say, that's not my purview. I deal with the entire ocean. I don't deal with individual water molecules. Um, so I wanted to show this video. In this video, we're going to zoom out from the field of view of an ocean to the Earth, solar system, galaxies, clusters of galaxies, and then I'm going to show you what I mean when I say the universe. All right, let's see. Oh, there was sound with this video. It's just some gentle music playing in the background. I thought I debated if I was going to speak during this. I thought that I would remain quiet and let people chill and watch the beautiful video. If the sound isn't coming through, I apologize. But there's only a minute left. Less than a minute. All right. So we're at the scale of galaxies. And I hope that you appreciate just how far we've zoomed out just to get to a single galaxy, from the Earth to the single galaxy, the Milky Way. And I'm not stopping the video yet. We still have a ways to go. You can see that galaxy distribution is semi-random, but it is random, but it's also clumpy. So galaxies tend to clump together into these super clusters. All right. This is what I mean when I say the universe. This huge, ginormous system of galaxies. All these little dots aren't even galaxies. These dots are super clusters of galaxies. So if you guys can see my mouse, hopefully you can. My mouse isn't covering one or two galaxies, it's covering 1 or 2 billions of galaxies. Billions and billions with a B. Um, as cosmologists, when we study the universe, we are studying systems of billions and billions to trillions of galaxies. This is another view of it's called the large scale structure of galaxies. This is just another coloring of the view that I ended on in the previous slide. And we've measured this to be true. Galaxies tend to cluster in these called filaments, and it's colloquially described as the cosmic web. So it kind of looks like a spider's web, a cosmic web of galaxies. And I think this is one of the most beautiful things, one of the most beautiful pictures. Uh, this particular image was made with simulations, but it is based off of real data. So we can see in the night sky galaxies are clustered in this way. And kind of the distances that we're talking about are hundreds of millions of light years. So this little box would be hundreds of millions by hundreds of millions of light years across. And at this scale, galaxies are like drops of water in a puddle. And that's a true statement. I did the math, and the ratio of one galaxy to 100 million light years is the same as the ratio of a single drop of water to a puddle. So if you're looking at a puddle, each water molecule in that puddle has its own life, has its own story. They're each doing their own thing. So the water droplets, one might be going right, one might be going up, one might be sinking down. Some of them are going to be spinning in every which way. Some of them are going to be rotating around. Maybe there's a small eddy or current moving them around. But if you're looking at the puddle, you're not looking at individual droplets of water. You're seeing the whole stationary, non-rotating puddle just sitting there in the pavement in front of you. Similarly, sometimes I've shown this image of the universe, of this large-scale structure of galaxies, to people before. And they say, well, aren't galaxies all moving? Aren't they all rotating? Shouldn't the universe then be moving and rotating? And it's just like water molecules, or droplets of water in a puddle. Each individual galaxy is rotating, it's spinning around. They're moving every which direction. Some galaxies are colliding with each other. Some are breaking apart. Each individual galaxy is doing all sorts of crazy things. But we really don't care about the individual galaxies because on average, for every galaxy moving this way, there's one moving this way, and it all cancels out. And then the universe itself is more or less a fixed system. So just as the puddle it's stationary, it's non-rotating, the universe, as far as we can tell, is non-rotating and fixed in space. Excuse me. This is what I mean when I say the universe. I mean collections of billions of galaxies on huge, massive scales. Scales that are so large that the individual dynamics, what a single galaxy is doing, is not important. We don't care if it's moving right or left or whatever, because on the average, statistically, those minor details average out. All right. Now that we understand what we mean by the word universe, we can start thinking like a cosmologist and asking questions about the universe as a system. So, when you're studying something, one of the first questions you can ask is, what is the shape? And I teased this question earlier. I said this is coming up. What is the shape of the universe? What does that even mean? That's such a weird thing to even think about. That's why I like being a cosmologist, because I think that it's really cool to think about things like this. The question, what is the shape of the universe, turns out, is directly related to the question, what would happen if you traveled in one direction forever and ever? So you pick a direction and you just travel for trillions and trillions of years, if not forever, in that one direction in, say, a rocket ship out in outer space. What would you run into? What would you see? There are a couple different options. Option one is that no matter how far you go, there's just more and more outer space. So space is infinite, and you keep on encountering more and more and more of it. That's option one. Option two is space is finite. There's a boundary. There's a wall or something. So as you're traveling through space, you're traveling past stars and galaxies, and then boom, you hit a wall, something that you can't pass. Or maybe it's a boundary between this galaxy or this universe and another universe. That's option 2. I'll tell you right now that that option is more in the realm of sci-fi and science fiction, because as far as we can look out pretty far, and we don't see anything that resembles walls, and there's no physical reason to think that there should be a wall just randomly out in the middle of space. That if you travel far enough, space looks the same pretty much everywhere you go. The stars around here are the same as the stars around here. There's no reason to think that if you go over here, you're going to run into a wall. It doesn't even really make sense to conceptualize what that wall could be. Or maybe it's a transition to another universe. So this second option is more in the realm of sci-fi. I left it in here for completeness, but cosmologists don't really think about this. It's not taken as a serious case. So one of the main options is you travel and the universe is infinite. No matter how far you go, there's more to go. Another option that is taken very seriously by cosmologists is that the universe is closed or periodic or spherical. All of these words are more or less synonymous with each other. Which means that if you travel far enough in one direction, you're going to circumnavigate the universe and end up back where you started. So like if you traveled far enough in one direction on the Earth, you're going to end up exactly where you started. The infinite and the closed cases, infinite and the spherical cases, those are the two main cases considered by cosmologists, and they're taken to be the most likely. There are many others. There are some really fun ones. Maybe if we have time, we can get into some of those. But infinite or spherical, those are the two options that are really taken seriously by cosmologists. So how do you figure out how large the universe is, or if the universe is infinite or if it's spherical? Well, if it's spherical, you can just travel in one direction and then you'll end up back where you are. And that sounds much easier than it is. In practice, we can see out roughly 45 billion light years away. And as far as we look, the universe doesn't appear to circle back on itself. So as we've never seen, the back of our own head looking at each other. We've never seen our location in the universe that far away. And we can also look 45 billion light years in each direction. And we've never seen, and if the universe was spherical, then we would see the same galaxy looking in both directions if it was within 45 billion light years away from us. And we don't see that. So short of circumnavigating the universe, is there a way to discover if it's curved, it's periodic more locally? And there is. So if you don't want to go all the way around, we can tell the shape of the universe by how objects change with distance. So this diagram on the left shows an eye viewing a galaxy, and it sees the galaxy at a specific size. If you look at a galaxy of the same size that's farther away, it's going to appear smaller. This is just a general fact that I hope you're all very familiar with. When things are farther away, they look smaller. They look smaller because they take up a smaller portion of your angular field of view in a flat plane. However, the story is different if you're talking about life on a sphere. So if the universe is curved, if you go far enough one way, you'll end up back where you started, then galaxies behave differently. So I had to draw this diagram myself, so the lines are a little janky. But if you see this one galaxy at a certain distance away from you, it takes up a certain angular field of view, and that is its apparent size that you can measure in real life. In a flat universe, as things get farther away, they get smaller. But in a curved universe, after a certain point, objects, as they as they first move away, so as this galaxy first moves away, it will start getting smaller. But after a certain point, it's actually going to start appearing larger. It's going to take up a larger angular view in your sky. And you guys can see this in the extreme example, as if something is as far away as it can get on the spherical in the spherical universe, it takes up your entire field of view. This is an extreme example. So if you were standing at the North Pole of the Earth, the farthest another human being could be away from you is at the South Pole, so on opposite ends. And from your position on the North Pole, if your lines of sight wrapped around the Earth, which they don't, but in this universe, they would, you would see your friend you were to measure your friend at the South Pole, would be in an equal direction. You could travel in any direction to get to your friend at the South Pole. I hope, that's just a simpler fact. And then if you can extend that to thinking about if you lived in a spherical universe, sorry about that. So if you lived in a spherical universe, where if you went farther enough around, you would get back to where you started. If there was a galaxy at the opposite end of you, you would see it in every single direction. So you would see it along these two lines of sight. You would see it along this if you looked in this direction, and you would see it along this direction. So its angular size would be 360 degrees. It would take up your entire field of view. So if you're watching something travel away from you in a spherical galaxy, it's going to get smaller, but then eventually, as it starts rounding around, its angular size is going to increase, and it's actually going to start to appear larger and larger. Extreme case, when it's on opposite sides, takes up your whole field of view. All right. I hope that makes sense. So this is what cosmologists do. They look at galaxies and they look at objects that we know how long they should be and know how far away they are. And we can tell what angular size they should be. By should be or what angular size they would be in a flat universe, and what angular size and if there's a deviation from that, if they look larger, then we've detected some curvature to the universe. So we can, with sensitive enough experiments, we could detect that the universe is curved or the universe is spherical without even going that far away if we had very sensitive measurements. All right. So cosmologists have done this extensively. They've done this a lot. And the jury, the verdict is that we don't have the sensitivity yet with our instruments to detect any curvature. So right now, the universe appears to be flat. So it appears to be saying it's flat is another way of saying it's infinite. So it appears that if you travel in one direction for long enough, you will just keep on encountering more and more universe. And the farther you go, and that is always the case, the universe is infinitely large. However, we can say that if the universe is spherical, it must be at least a diameter of, I'm forgetting, I believe 200 trillion light years. I have it written down. 200 trillion light years sounds right. Oh, not 200, 20. So we can see 45 billion light years around us in any direction. And that region looks locally flat. But it might be the case that that's just like the Earth looks flat if you only see a small portion of it. It might be that the universe is actually spherical. If you went far enough, you would come back to where you started. And all that we can say is that if the universe is bounded, if it is spherical, you would have to travel at least 20 trillion light years before you end up back where you started. And as we get more and more sensitive measurements and better telescopes to measure these kinds of things, we can whittle that number down and get a more and more, we can get more constraints on that number. Is there a galaxy size ladder to calibrate these measurements? Okay, yes, I knew that this was a sophisticated audience. There is a galaxy size ladder, also a galaxy distance ladder. All right. It's ultimately, however, these aren't really done with galaxies. These are done with the size of spots on the CMB. Which I wasn't really going to talk about this because it is more advanced. If you know what the CMB is and you know what the spots are, then hopefully that sentence made sense. But it is, so we don't necessarily use galaxies. I just use galaxies because it's as a pedagogical tool. In real life, we would use okay, how about this? This is also true. So either spots on the CMB. If you're not familiar with spots on the CMB, that's fine. We would use the length of these superclusters of galaxies. So each of these threads is a specific length, and we can calculate what the statistical, each thread should be on average. So remember, these threads are filaments of superclusters of galaxies. So they're super collections of galaxies that are arranged in like kind of a web-like threads, tendrils. And we can do some fancy math and physics and science, and we can calculate how large these tendrils should be on average. And we can also calculate some other statistical length properties about these superclusters of galaxies. So we can say, on average, how far... Okay, another thing that we can say is, you see these bright spots? We can calculate, on average, how far apart we expect those bright spots to be. And then we can use that as a standard ruler. So there's not, so your question, is there a galaxy size ladder? There's really there's not a galaxy size ladder, but there are standard rulers. If you're familiar with standard candles, there are standard rulers. They're usually statistical standard rulers. So we can say on average super clusters of galaxies should be this far apart. We measure how far apart they are on average. And then we can get a standard ruler from there. Okay, that's a little bit more advanced. I hope that that made sense. Okay, cool. How can we tell the shape based off of how angular size changes? Okay, so the universe is either infinite, or if it repeats, you'd have to travel at least 20 trillion miles before it repeats. We are not, or more. We're still figuring out which it is. If anybody else has a question, it's a good time to put it in the chat before I move on to the next section. So we talked about how the universe is changing with space, its spatial distribution. I wanted to talk a little bit about how the universe is changing with time. You guys have probably heard that the universe is expanding, and that it's constantly getting larger, and it used to be much, much smaller. This is a really helpful diagram to kind of illustrate what that means. As the universe gets larger, it's the space between galaxies increases. So if the universe is spherical, if it's like a sphere, there's a nice geometric interpretation for what it means for it to expand. So it's like a ball blowing up, like a balloon getting larger, or a balloon shrinking, getting smaller. So that's a nice geometric interpretation. And then you have a real size, physical size that's increasing or decreasing. I get this question a lot, which is, okay, if the universe is infinite, which we think it might be, how can it expand What is it expanding into? What does that even mean? And I give this example of something that's infinite and expanding. So imagine you have an infinite ruler that's infinitely long in both directions, and you have regular tick marks. So you have tick marks every inch. And then you take that ruler and you spread it out, you stretch it. And as it stretches out, those tick marks move. So instead of being every inch, they become every 2 inches. What just happened is you took something that was infinitely long and you stretched it. There's no other way of saying it, but you stretched it, you expanded it. But you didn't expand it into anything. It was infinitely large before, and it was infinitely large after. So it's the same size, but it's the distance between those tick marks increased. The universe is similar. So if the universe is truly infinite, then we have an average spacing between galaxies. And as the universe expands, the spacing between galaxies increases. And galaxies will tend to move apart from each other, which is an observable fact. It's something that we see happening in real time all around us. So the universe isn't, if it's infinite, it's not expanding into anything. It is just, it was infinite before and it's infinite after. So it's the same size, but it's still expanding, which is kind of weird to think because infinities are weird. I hope that you guys are having as much fun as I am. I love thinking and talking about things like that. And I love saying things like, yeah, the universe is the same size, it's just expanding, which doesn't make any sense, but it does when you think about it because it was always infinite. Gonna wrap up in just a couple minutes. Before I do, I wanted to just talk about the Big Bang briefly and address some common misconceptions. So the main thing I see online and I hear from people is they will say, okay, so we know that the universe is expanding. This is true. It's getting larger with time, or it's actually maybe it's the same size, but the distance between objects is getting larger with time, which means that if we go backwards in time, it was compressed, it was shrunk. So distances were smaller in the past. This is also true. And then they say that if you take this back to the Big Bang, what the Big Bang is the universe popping into existence and when it was infinitely small and infinitely dense. This is not true. This is not what the Big Bang says, or the Big Bang theory. This is not what cosmological models say. This is not what the main cosmological models say. I'm sure you could maybe find one or two cooked up models that say something crazy. But this is not what the main cosmological models say. This is not what the standard Big Bang model theory says. This is a true statement that the universe at the Big Bang, or at the excuse me. This is a true statement, and I'm being careful with my words. 14.8 billion years ago, which is, oh, by the way, I'm sorry, I did a bad job talking about what this diagram is. I'm going to go back to this. This model kind of has the universe shrinking to a point of to the Big Bang. And this Big Bang occurred roughly 14.8 billion years ago. And this is a true statement. So 14.8 billion years ago, the universe started expanding. And before it started expanding, it was much smaller than it was today. It was at least, I want to get this number right. I believe it was 100 trillion septillion times smaller. Yes. So 14.8 billion years ago, the universe was 100 trillion septillion times smaller than it is today. And at that time, it started expanding. This diagram does a pretty good job of this point that's kind of shrouded in light. That was 14.8 billion years ago. The universe was 100 trillion septillion times smaller. It started expanding rapidly, and then it went through a brief period of rapid expansion, and then it's been expanding slowly ever since. those are all true statements. So I will wrap up in just a second, but I said it was 100 trillion septillion times smaller than it is today. So then the question is, well, how large is it today? And we don't know. It might be infinitely large today. And if it's infinitely large today, then when it was 100 trillion septillion times smaller, it was also infinitely large. um, so many people think that the Big Bang, the universe was infinitely small, or it took up no space. That's not necessarily true. That's not what the Big Bang model says. If it's infinitely large today, then it was also infinitely large at the Big Bang, but it was just much more compressed. So 100 trillion septillion times more compressed, and also hotter, so much hotter. People also think, this is a misconception, that the Big Bang was the start of time, so that the universe came into existence at that moment. That is another misconception. This white light here signifies that we don't know what's going on. So all of our models break down 14.8 billion years in the past, and we don't know what occurred before the Big Bang. That's an ongoing question that we're trying to answer. What happened before the Big Bang? Was there a before the Big Bang? Did time exist before the Big Bang? These are open questions that we don't know the answer to. Most models say that there was a before the Big Bang, and we just don't know what was going on. We still have some hypotheses. But the statement that the Big Bang is when the universe was infinitely small and popped into existence and was infinitely small, that is not what models say. All right. This was a heavy topic. I hope that you guys enjoyed it and had fun thinking about some of my favorite things to think about. We have a couple of minutes for questions, I think roughly 10 minutes. So if anybody would like to unmute or type in the chat, I'd be happy to answer questions.
At what scales will we recognize the proverbial back of our head?
So I heard, at what scales will we recognize the proverbial, what was the end?
Back of our head.
I'm so sorry. Could you type this in the chat? I'm really having trouble with the audio. It's just breaking up a lot.
At what scales will we recognize the proverbial back of our head?
Oh, will we see the back of our head? Okay, so um uh the universe, if it is periodic, so if we could see all the way around it, or if we could travel all the way around it, we would have to travel 20 trillion light years. Yes, that's what I said. 20 trillion light years. And that would take 20 trillion years for the light from the back of our head to go all the way around, and then we'd see it in our eyes. And the universe, I mentioned, has only been around, or has only been expanding for 13.8 billion years. So it would take 1,000 times larger than the age of the universe for us to send light the long way around the spherical universe and see the back of our heads. So that's probably not going to happen. Which is why this method of calculating of angular distance versus true size versus angular size versus true size versus distance. That is how we're going to measure any curvature. Great question, though.
Can you hear me?
Your early charts contained the very large structure Laniakea. How many structures are we now aware of? That's a good question. I'm not sure. So we're aware that thousands of these structures, roughly, I don't know if it's actually thousands, but many of these structures, hundreds to thousands of these structures, uh, exist because we can tell how large they are, and we know that they're filling up the universe, and we know if the universe is infinite, then there's an infinite number of these structures. Excuse me. How many have we named? I'm not actually sure. That's a good question. I would have to look that up. Probably not many. I would guess that you could count them on one hand. I'm not actually sure. I'd have to look that up though. As in named and like um measured completely. Or well, what is your position on some people's beliefs that our current universe may be inside of a black hole? What's my position on a belief? I mean, people are allowed to believe whatever they want. It's almost uh I don't want to be a jerk and be like, you can believe what you want, but that's not what science says. Um, it is the universe is not in a black hole in kind of that sense of the word. However, it is certainly true that the universe as a system shares a lot of similarities with black holes. So, black hole is a region of space-time that once you enter, you can never leave. The universe, and it has a physical singularity. So the black hole at the center of a black hole, the physical location of its center, has a singularity. We think it has a singularity. Our models say that it has a singularity. Our best models, which aren't that great. Okay, this picture of the universe, there are some similarities. So the universe is a region that nothing can come into the universe, kind of by definition, because the universe encompasses everything, nothing can come in. So kind of the opposite of a black hole where nothing can leave, nothing can come into the universe because it is everything. And then the universe also contains a singularity, not in space like a black hole, but in time. So at its early time, our models say that the universe approaches a singularity. It's not a true singularity in the sense that it's like infinitely small. We don't think it's infinitely small. Most our standard theories don't say it's infinitely small. I'm trying to be careful with my words. But our best models say that it approaches a singularity at a time, so a temporal location, whereas a black hole has, our models say that it approaches a singularity in a spatial location. So there are some parallels between the two, uh, and then some, media sites grab that and ran and say like, oh, the science says that the universe is inside a black hole. Science does not say that, but there are many parallels between the two systems. Great question, by the way. So oftentimes people who study the universe also study black holes, and actually I study black holes and the universe because they are, yeah, there are many similarities between the two. Great questions, guys. This is a great group. All right. Yeah, this has been a great group. It's been a great, absolute pleasure to present to you. There's another question.
How about a question about the shape of the universe on a larger scale? If inflation happened in the first picoseconds of the universe, and there is a vast amount of the universe outside the observable universe, how does that change our picture of the curvature of space and the time to see the back of your head, et cetera, et cetera? It's a very confusing picture.
Yes. Okay. Yeah. So everything I said is accurate, that if space is curved, it would have to be 20 trillion light years around. And then this is a good video or a good image. If it is curved slightly now, it was more curved earlier in the universe when it was smaller. So When the universe was much smaller, it was tighter, and you would have had to travel much less to go all the way around. Um, so your question of, okay, I believe your question was, so if we wanted to circumnavigate the universe, we would have to travel for 20 trillion years at the speed of light, um, to go around. But the universe is also expanding, so wouldn't it take, even longer? So as we're traveling, the universe would be expanding, and then it would take much longer than 20 trillion years. Yes, this is exactly the case. That is exactly true.
Different question. If there was cosmic inflation in the first picoseconds of the universe, there is a vast amount of universe outside of our observable universe and our 13, 14 billion year or 44 billion year distance, as you want to decide. The universe could be trillions or quadrillions of times that large. So how does that affect the curvature of space? Are we talking about the curvature of space within the observable universe or in the totality of the universe? Because most of that universe will never be observable by us.
Oh, this is a great question. So, no, this would be the curvature in the entire universe. We know that the observable universe isn't spherical because we can see to the end. Um, and if just the observable universe was spherical, then we would be able to see um, multiple repeats of galaxies. So we'd see the same galaxy in multiple locations because we're seeing it around multiple views of the observable universe. Um, so we know for certain that the if the universe is spherical, it's not the observable universe. The observable universe would just be a small part of the whole universe, which would be the spherical, or it could be not spherical, it could be infinite. Great question. Does that answer everything?
Sure. Yes.
Yeah, and then inflation would also reduce the amount of curvature that we have, making it seem pretty close to flat. So, yes, it would go from more curved to locally flatter. Yes. Yeah, so the observable universe is 45 billion light years in radius. And then if the universe is the whole universe is spherical, it would have to be 20 trillion light years in circumference. So that is much, much larger. Okay. All right. This is a good group. You guys are getting it.
I want to rephrase my question about the proverbial back of your head. What I was getting at is we've got New Horizons and the Voyager missions. Those are what are the furthest away from Earth that could look back and see us and get a picture of what the back of our head looks like. I'm sure scientifically we have a decent picture of what things look like, what we look like, or our galaxy or solar system. So I'm trying to get an idea if what scales we have good data as far as could we recognize the proverbial back of our head if we saw it. Obviously, we're looking back in time as well.
Yeah. Okay. Yeah. The back of the head is not realistic unless the universe is like 1,000 light years in diameter. If it was, then you would see the Earth. You would look out, and then 1,000 light years away from us, you would see the Earth as it was 1,000 light years ago. And then if you look out 2,000 light years, you would see as the Earth as it was 2,000 light years ago. And then that would be yeah, you would literally just see the Earth. So you could see the Earth 4,000 light years away, 4,000 light years ago, or 4,000 years ago, and you would see the first civilizations forming. So you could look with a little telescope and you would see, people building Babylonia, or Babylon, um, Babylon. But we know that we've looked and we haven't seen the Earth 1,000 light years away and 1,000 light years ago. So we know, and we've also done fancy math, and we know that the universe is at least 20 trillion light years in diameter, which means that we'd have to look 20 trillion light years away, and then we'd see the Earth as it was 20 trillion light years ago. But 20 trillion is roughly 1,000 times longer than the age of the universe. So that's not going to happen. That's not observable. Does that answer your question?
Somewhat, yes. Like,
But yeah. Uh, yeah, and you would see kind of like a not a ring, a shell of Earths. So everywhere you looked, so if the universe was 1,000 light years in diameter, every direction you went, you would circle back to your original spot. So when you looked at the night sky, if you look 1,000 light years away, any direction you point your telescope, you're going to see the Earth 1,000 light years ago. I don't know what side of the Earth you would see. You would see some side of it. Doesn't really matter. Um. So yeah, there would be like a dome of Earth of light from the Earth 1,000 years ago at that distance, and then there'd be a second dome 2,000 years ago, farther distance. Does that make sense? It's crazy to think about. I love thinking about this. All right. I know it's 9, so moderators just
We got
let
one
me
more
know
question
if
in the chat.
I'm happy to answer. I'm happy to stay late and answer any questions that there are, but I want to respect your time. So whatever works for you guys. Okay.
Yeah, there's one more question in the chat.
All right. Might a disparity in the expected lensing geometry of a distant source one day be used to infer curvature? So, disparity in the expected lensing geometry of a distant source one day be used to infer curvature. One second. Okay, yeah, distant. I thought so. So the lensing geometry is the amount that light bends around a massive object. So we would expect light to bend a certain amount around a distant object. And you're saying if it bends more or less than we expected it would, the expected source one day be used to infer curvature. Yes. Okay. Yeah. Yeah. So, so on in flat space, parallel lines never intersect, but on a curved space, parallel lines do intersect. For example, if you have two parallel lines at the equator and they both point up, eventually they're going to merge at the North Pole. So parallel lines do intersect, and so the angles of lines on a curved surface, the way angles behaved on a curved surface is fundamentally different from the way angles behaved on a flat surface. So your question is lensing is you have a massive source that bends, that angles light rays in a specific manner. If that is far enough away, then the geometry, so say it bends those light, we would expect it to bend the light rays to be parallel to each other. Well, then in a curved geometry, those parallel lines are going to intersect, whereas in a flat, there wouldn't. Reasonable estimate of the lensing mass. So yes, there would be an additional factor based off of the curvature and how those light paths travel. Would that be used to infer curvature? I think that if you're at that point where you can measure the distance and the mass of a distant object well enough, then we would probably have detected curvature already via other means. The way that we are going to detect curvature is probably going to be looking at the most distant objects that we can see, which is the CMB, and it's going to be looking at the average size of those spots on the CMB with better and better measurements. Believe. But yeah, that would be a factor. So this is, of course, we require a reasonable estimate of the lensing mass. Yeah, it would be a factor. I don't know if that would be easier than the angular size method. Angular size method is pretty tried and true. But yeah, maybe. I'm not actually sure how we're going to do it or if we'll do it. Okay. Thank you guys so much. This has been a really lovely group to present to.
Thank you, Simon.
Sorry for going a little over. I'll hand it back to you guys.
That's right. Ran it in, I believe.
Nice. Simon, thank you so much.
Thank you very much.
Thank you.
Yeah, of course. Thank you guys.
What's it like outside? Rick? See some.